So here's one more video about irrational roots and what we might be able to prove about them. So the statement is, suppose that a, b, c, and d are rational numbers, and a plus b root 2 is equal to c plus d root 2. We want to show that a equals c and b equals d. First, just briefly, why would we be interested in this? This is really a foundational thing of what's called algebraic number theory, where we consider exactly combinations like this: a rational number plus a rational number times root 2, and sometimes maybe an integer sometimes a half integer plus an integer times root 2. And I want to make an analogy here. What we're saying is that there's no way root 2 is so different from rational numbers. It's not just that it happens to not be rational. It's so different from rational numbers that I can't play the coefficient, play 1 and root 2 off against each other. This is like a times 1 plus b times root 2. I can't play them off against each other in a creative way to get an unexpected combination of 1 and root 2. That any time I take two different numbers, a and b, root 2, and then I change either of the numbers, I really get a genuinely new number. So it's saying something fairly profound about root 2. It's very analogous. Analogous to complex numbers, where you take a number plus b times the square root of minus 1, or a plus bi. And I'm not assuming you know a whole lot about complex numbers, but the more you know about complex numbers, the more you're familiar with the idea that two complex numbers are only equal if the real part and the imaginary part are individually equal to each other. And that lets us think about things like the complex plane, where a plus bi sits here and a sits on the real line and bi sits here. Okay, there's a lot of value to that idea, and it's really that I is some really very, very new number. Here, root 2, if we are thinking of our home base as rational numbers, root 2 is a new number in almost the same way, that it just sort of comes out of the blue. If you only ever heard of rational numbers, and the only coefficients you can put in front of them are rational numbers, root 2 is this new, very independent kind of gadget. So that's a little bit about why we'd ask this problem. I took this out of the book, and I wanted to gloss this and sort of explain why would they be asking us to prove this. It's a really basic result. Okay, so I want to show two things. I want to show that the ordinary, you could say this is like the ordinary part, and this is the rooty part. That the ordinary parts have to be the same, and the rooty parts, the coefficients of root 2, have to be the same as well. To show two things, I could try to show them all at once, but it's probably more straightforward to show one and then show the other. And so I'm going to show this first by contradiction. Okay. And here's why that's a good setup. Even if you didn't sort of know how to start the logic of this proof, and this is an important thing about discovering proofs for yourself, sometimes you don't want to worry too much about exactly, is it a proof by contradiction? How do I set the logic up? Just, if you have an equation, manipulate it and play with it. Don't pretend that you are writing down the steps of your proof right away, but just manipulate it and see what kind of manipulations might be useful, and that might tell you what kind of logic is going to be useful. Here's why assuming b is not equal to d is going to be very useful. I'm going to isolate root 2 here. A minus c is d root 2 minus b root 2, or it's root 2 times the quantity d minus b. So in other words, root 2 can be written as a minus c over d minus b. Hey, wait a minute, I could not have done that if d and b were equal. And so that's what really tells me, hey, you know what? It's a great idea. Well, wow, what a great excuse to start a proof by contradiction of b equals d. The fact that I would really prefer to be able to assume that d is not equal to b. So I'm going to assume that b is not equal to d, and I get this expression, well, duh, the difference of two rationals is rational, the difference of two rationals is rational, the quotient of two rationals is rational. We haven't proved that super carefully, but we're assuming that we know that kind of simple fact. And there's our contradiction, because we know root 2 is not rational. Okay, so that does... So this shows that, in fact, b does have to equal d. Okay. And then the rest of it's equal. Hey, if b is equal to d, okay, I'm just going to go back to any one of these expressions, but hey, like here, okay, hey, that's equal to 0. Let me be a little more careful. it's bad style to go back up and write things here. Then a minus c equals root 2 times d minus b. But that's 0. So in fact, a has to equal c. So the only way you can get this kind of equality is not accidental. It has to be intentional. It has to be that the ordinary parts, the parts that you're just multiplying by 1, you could think of, are equal, and the parts you're multiplying by root 2 have to be equal as well.